This is a problem on successive ionization energies. It will explore your knowledge on how to use this concept when you're solving chemical problems. The problem is, which element would you expect to have the lowest third ionization energy, i.e. 3? Take a few minutes to think about this problem, propose a solution, and start working on that. Once you finish working on your solution, compare with the solution that will be described shortly. The plan to solve this problem will consist on, first, write the electronic configuration for each of the elements in question in their ground state. Second, write the reactions indicating the first ionization energy, IE sub 1, the second ionization energy, IE sub 2, and the third ionization energy, IE sub 3. The third step is to identify the sub-energy levels from which each electron is removed when the IE sub 3 is in question or is being considered. The last step will consist of looking at the quantum number n that will indicate the energy level and the effective charge ZF to rank the elements based on their third ionization energy. So the first step is to write the electronic configurations of the elements that are in question here. So we will start by writing the electronic configuration of potassium, and we are going to use the condensed nomenclature. We have to remember that potassium has an atomic number of 19. That means that we will also have 19 electrons. The shorthand that we will use is we'll use argon, electron configuration of argon, and then after that we add 1 4s electron. For calcium, the atomic number is 20. The electron configuration will be that of argon, followed by 4s2. And for scandium, the atomic number is 21. The electron configuration will be that of argon, followed by 4s2, 4p1. The next step will be to write the reactions indicating the ionization energies. And let's take as an example the one of potassium. And we will do is, as well, we will define, before we do that, we'll define what the electron configuration of argon is, because that's going to become important. So for argon, the electron configuration is that of neon, 3s2, 3p6. Okay, so now the first ionization energy of potassium. So that means that we're going to go from potassium to potassium plus, which releases 1 electron, and that corresponds to the first ionization energy. This leads to, if we compare the electronic configuration of potassium, when we lose 1 electron, we are going to have an electronic configuration which is going to be equal to that of argon, and all the 4s electrons are basically gone. So for the second ionization energy, we're going to have a transition that goes from potassium ion, potassium 2 plus, releasing 1 electron, and because now we have to remove 1 electron from the electronic configuration of argon, we are going to be using that one from argon and represent the electronic configuration corresponding to argon, which in this particular case will be that of neon, 3s2, 3p5. For the third ionization energy, which is the main topic of this problem, we now begin with the potassium 2 plus ion that will lead to potassium 3 plus plus 1 electron. The third electron ionization energy will correspond to the energy needed to do this transition, and the resulting electron configuration is going to be, or electronic configuration is going to be 3s2, 3p4. So in order to continue solving this problem, then, we're going to have to take into account how much energy is really needed to take into account the different processes. So we're going to really mainly focus on the electron configurations that we have, say, between the K2 plus, which is represented by this one over here, and K3 plus, which is represented by this electronic configuration over here. Now that we have already done or figure out the processes involved in the third ionization energy for potassium, we are going to start working on that one for calcium. For calcium, the first ionization energy corresponds to the formation of calcium ion plus 1 electron. The electronic configuration that we'll have for calcium ion plus is that of argon, and 4s1 electron. For calcium, for the second electron ionization energy, calcium plus is going to lead to the formation of calcium 2 plus 1 electron. The electronic configuration is going to be that of argon, and we have lost the 4s1 electron, so that's all what we have. And for the third ionization energy, calcium 2 plus will lose 1 more electron, and that will have to give the configuration of the neon gas, 3s2, 3p5. Basically, we are losing 1 electron from the electronic configuration of argon. The third one that we will do is that of scandium, and we follow exactly the same process. We start with scandium. It ionizes to form scandium plus 1 electron, and the electron configuration for scandium will be then that of argon, and 4s2. The second ionization energy, scandium ion, to form scandium 2 plus 1 electron, and the electronic configuration for scandium 2 plus would be that one of argon, 4s1. And the third ionization energy will be that of scandium 2 plus, forming scandium 3 plus ion, plus 1 electron, and the electronic configuration would be that one of argon, and we lose the 4,1s electron. So now, with this information, we have for each of these 3 elements and their third ionization energy, we have the electronic configurations from the second to the third, and we will combine them all so that we can actually understand and provide a rationale for the order of ionization energies, the third ionization energy, that is. Okay, so the work that we did to figure out what transitions are involved in the third ionization energy of potassium, calcium, and scandium is summarized in this new slide here. We have the reaction for potassium, the reaction for neon, the reaction for, I have to start again. The work that we did to derive the third ionization energy is summarized here. We have the reaction for potassium, the corresponding electronic configurations, the reaction for calcium, the corresponding electronic configurations, the reaction for scandium, and the corresponding electronic configurations. So in order to determine which one is the lowest third ionization energy, we will take into consideration two factors. The one factor will be the quantum number n, which involves energy, and the second factor will be that involving the stability of field or half field sublevels. So let's see what I mean by that. So if we consider the case of potassium versus the case of calcium, we see that the third ionization energy involves losing an electron from the 3 pi orbital to form a new electronic configuration, which gives to the 3p4 orbital. Now, if you compare that with that situation for calcium, we have losing an electron from the 3p6 to give a 3p5. There is nothing particularly special about this except for the atomic number for calcium is larger than potassium. Let's recall that the atomic number for calcium was 20, and that for potassium is 19. So this involves that if all of a sudden we consider this higher number of positive charges in the nucleus, that this ionization energy is going to be higher in energy. So, this potassium will be potentially the lowest at this point, or lower than that of calcium. Now, the other comparison that we would like to do is between, say now, potassium and scandium 2+. So for that, what we need to look at is the changes that happen in the electronic configuration for the third ionization energy. We are losing one electron from the 4s1 to forming a 3p6 field or fully full electronic configuration or orbital. That means that in this particular situation, we have a stable, very stable system here, and that additional stability provides a very low energy, the ionization energy. So we also can see that that everything that was lost in this particular case was an electron from the 4s, which is farther away. So n is important here, which is easy to lose to form a stable configuration. Now, so this is the lowest because it's much lower than any that happens above. As a confirmation, one could potentially look at tables in which the third ionization energies are compared or are provided, and we can find in those tables that the third ionization energy for scandium is 2,389 kilojoules per mole. For calcium is 4,912 kilojoules per mole. And for potassium is 4,420 kilojoules per mole. So clearly, the lowest ionization energy, third ionization energy, is that corresponding to scandium. And scandium is the answer to this problem.